Welcome to 86th lecture. We are studying transient analysis, and in this lecture we will continue solving an example we started last time in CA85. This is the example where we have these number of sources, this current source, this is a 3 amperes current source, and resistors, these two resistors and a capacitor. And we have to find the voltage drop across capacitor for all times. In last lecture, CA85, we computed VC at 0 minus, and it remained the same at 0 plus even, because we know that the voltage drop across capacitor cannot change all of a sudden. It was 60 volts. And at infinity, VC was computed to be 24 volts. In this lecture, we'll continue solving this problem, and we'll find a general expression for VC of t for all times t. Right. For that, we have to see what the circuit is after we have closed the switch. The switch was closed at time t is equal to 0. If it is closed, this 3 ampere circuit is this 3 ampere current source is no more in the circuit because its upper and lower ends are short circuited together. Therefore, they are not in the circuit, and this 4 ohm resistor is directly connected to ground. So we have a ground here, right? And the same ground that we have here. So now this 4 ohm resistor, the lower end of this 4 ohm resistor is connected to ground, and these two 4 ohm resistors, they come in parallel with each other, and the remaining circuit is the same. And then we have to solve this using the cloud node or super node technique that we have discussed earlier in this course. A cloud node is a node when we have voltage source or voltage sources directly in between two nodes, and there is no other element, resistor or capacitor or inductor. There are only voltage source or voltage sources between two nodes. So these V1 and V2, they form a super node, and then we draw a cloud around the super node and see what are the connections that are outside of this cloud. This one, the second, this third. So we have these three, and these two can be combined together, because 4 and 4 ohm resistors, when they are connected in parallel with each other, they become 2. 4 in parallel with 4, it's 2. So there are only two branches connected with this cloud outside of this cloud. This 2 ohm resistor, the parallel combination of this 4 and 4 ohm resistors, and the current through this 2 farad capacitor. So V1 by 2 is the current flowing through the combination of these two resistors, plus 2 IC times dV by dt of V2, because V2 is the voltage drop across this capacitor. And this is simple. This is a simple differential equation, and which we call as equation number 1. For equation number 2, we know that V2 is V1 plus 24 plus 2VA, plus 24 plus 2VA, but VA is the same as V1. So instead of VA, we can put V1 here. So if we put VA is equal to V1, V2 comes out to be 3V1 plus 24. V2 comes out to be V1 plus V1, 3V1 plus 24. Right, we can solve it further, and we can write everything in terms of V2. So V1 is equal to V2 by 3 minus 8. By rewriting this equation, we come to the point where V1 is equal to V2 by 3 minus 8. Right, and then we can put this equation number 2 in equation number 1. What is equation number 1? This first differential equation. Instead of V1, we put V2. Instead of V1, we put V2 by 3 minus 8. So putting V2 by 3 minus 8 gives us another differential equation in terms of V2. This is quite advantageous to have this equation in terms of V2, because V2 is the same as VC, and this is our desired quantity. V2 is the same as VC. So we have taken everything in terms of V2. So now it's quite easier for us, because computing V2 is actually computing VC. Or we can write V2, since V2 is the same as VC, so V2 can be replaced as VC of t, and the same equation can be written by replacing V2 with VC of t, our desired quantity. And then we know that we have been solving that this VC of t, since this is a differential equation with a constant term on the right hand side, it's a first order differential equation with the constant term on the right hand side, the general solution is k1 plus k2 e to the minus t over tau. And we know that putting the initial and final conditions, we can compute k1 and k2. So putting t is equal to 0 is k1 plus k2, because this term becomes 1, is equal to 60. Why 60? Because Vc of 0 is 60. We computed in last lecture. Vc of 0 is 60, but Vc of infinity is 24 volts. So putting this gives 60, and then if you put Vc, if you put t is equal to infinity, Vc of infinity is 24, and the second term k1 plus k2, this term becomes 0. So k1 is 24, this means k2 is 36. So we have now computed two of the three unknowns, k1 and k2, and the final unknown is tau, that we obtained by putting this equation number 5 in our basic differential equation A, this one. Putting this and solving the derivative term gives us tau equals 12, or Vc of t is 24 plus 36 e to the minus t over 12. Right. So how is this plotted? We can plot this by, if you put t is equal to 0, this term becomes 1, and this is 24 plus 36 means 60. So this is 60. And if you put t is equal to infinity, this term becomes 0. So 0 times 36 is 0. So 0 plus 24 is 24. So this is 24. So at time t is equal to infinity, the value is 24. So, and this decreases like this. So at time t is equal to 0, this is 60, but for time t is equal to infinity, this becomes 24, because the second term becomes 0. So this is t, and this is v sub c of t plotted versus t. Right. That's all for this lecture. Thank you very much.